Doping concentration is provided 10 raised to the power 16 per centimeter cube, and it is assumed to be fully ionized. Therefore, whole concentration can be assumed to be equal to acceptor impurity concentration, which is 10 raised to the power 16 per centimeter cube. Generation rate is provided to be equal to 10 raised to the power 20 per centimeter cube second. Recombination lifetime is provided to be equal to 100 microsecond. Intrinsic carrier concentration is provided 10 raised to the power 10 per centimeter cube. For steady state, generation rate is equal to recombination rate, and recombination rate is equal to excess charge carrier concentration divided by recombination lifetime. Generation rate is provided 10 raised to the power 20 per centimeter cube, and recombination lifetime is given 100 microsecond. Therefore, excess charge carrier concentration is equal to 10 raised to the power 16 per centimeter cube. By mass action law, you can also find the thermal equilibrium free electron concentration to be equal to square of intrinsic carrier concentration divided by whole concentration, which will give 10 raised to the power 4 per centimeter cube. You can see that the excess magnetic carrier concentration, which is free electron concentration, is significantly greater than thermal equilibrium free electron concentration. Therefore, we can assume that the net free electron concentration is approximately equal to excess carrier concentration, which is 10 raised to the power 16 per centimeter cube. But for the net whole concentration, we can see that excess charge carrier concentration is comparable to the thermal equilibrium whole concentration, and have to add both these concentrations. Now, the product of carrier concentration can be found to be equal to 2 into 10 raised to the power 32 per centimeter raised to the power 6. So, this is our final answer. We know that energy is equal to Q into V, where Q is the charge and V is the potential difference. Energy is provided to be equal to delta, so we can write that the potential difference across the ends of the semiconductor is equal to delta upon Q. Also, we know electric field is equal to minus V upon distance L. Since the magnitude is asked, we can ignore the minus sign, and by putting the value of potential difference delta upon Q, we can find the magnitude of electric field. Length is provided to be equal to L. Therefore, magnitude of electric field is equal to delta upon QL. So, the answer is first option. Optical generation rate is provided 1.5 into 10 raised to the power 20 per centimeter cube second. It is provided that the illumination is taken uniformly. We also know for the semiconductor to be in equilibrium, the optical generation rate is equal to recombination rate, which is further equal to excess concentration divided by carrier lifetime of magnetic carriers. And here, since the semiconductor is N-type semiconductor, the magnetic carrier will be whole. So, the lifetime that will be used will be of whole. Now, you have to simply put the values. So, the excess whole concentration at time t is equal to 0 comes out to be equal to 1.5 into 10 raised to the power 13 per centimeter cube. The incident radiation was uniform until the time t is equal to 0. Also, we can assume the Hall concentration is nearly equal to the excess Hall concentration, as the thermal equilibrium Hall concentration will be significantly smaller than the excess Hall concentration. So, at t is equal to 0, the Hall concentration will be equal to 1.5 into 10 raised to the power 13 per centimeter cube. Now, we also know the Hall concentration will decay with the formula. Now you have to simply put the values. After calculating, you will find the Hall concentration at 0.3 microsecond to be approximately equal to excess Hall concentration, which is 7.46 into 10 raised to the power 11 per centimeter cube. So, the answer is the first option. Now, for the region, the continuity equation will be since it is provided in the question that the electric field is 0, therefore the terms relating the electric field become 0, and also since the semiconductor is in steady state, the differentiation of excess carriers with respect to time will also be 0. That's how we got this continuity equation. Now we can modify this equation to recombination rate and generation rate both are provided in the diagram, and after putting the values we will get. Now we are going to integrate this equation with respect to x, which will give now we will integrate it again, which will give the excess free electron concentration let these two equations be first and second. Now due to symmetry we have excess free electron concentration at distance Ln on either sides from the midpoint to be equal. Putting the values for excess carrier concentration from the second equation, we will get so we get the coefficient C1 to be equal to 0. Therefore, we can modify the first and second equation to let the resulting equations be 3 and 4. Now we will write the continuity equation for region x greater than Ln and smaller than 2Ln. You can see from the graph that generation rate and recombination rate both are equal to 0. Therefore, the resulting continuity equation will come out to be. Double integrating this expression, we will get the excess carrier concentration to be equal to Ax plus V, and at x equal to 2Ln, excess carrier concentration is 0. as at the boundary the carrier concentration is assumed to be 0. Therefore, we can write excess carrier concentration like this. If you differentiate it, we will get let this equation be 5 and this equation be 6. Now you know that these two equations were valid for x equal to or greater than 0 and equal to or smaller than ln. So you can see that at ln we have two equations for excess carrier concentration as well as two equations for differentiation of excess carriers with respect to x. So we will equate the differentiation of excess carriers with respect to x from equation 4 to the equation 6 and will take the value of x to be equal to ln. Also, from equation 6, we have now the magnitude of diffusion current density due to free electrons can be found out to be equal to charge multiplied by diffusion constant of free electron multiplied by gradient of free electron concentration. We just found the value of gradient. We have to simply put the value. After calculation, we will find the diffusion current density due to electron to be equal to 2.1886 milliampere per centimeter square, which can also be written as 2.19 milliampere per centimeter square. So this is our final answer. We know that electron current density is sum of diffusion current density due to electron plus drift current density due to electron. Diffusion current density due to electron is equal to Q multiplied by diffusion constant of electron into concentration gradient of electron, and drift current is equal to unit electronic charge Q multiplied by mobility of electron multiplied by electric field multiplied by free electron concentration. First we will find the value of E. Energy is equal to QV. Also we know that electric field is equal to minus V upon X, or we can write V is equal to minus EX. So energy is equal to minus Q into X into E. We can see energy divided by distance x is actually equal to minus Q into electric field, and the term on the left hand side of the equation is nothing but slope of energy versus distance graph. Slope is provided minus 0.1 electron volt per centimeter. Since we are talking about electron, charge will be negative, which will eventually give us electric field to be equal to minus 0.1 volt per centimeter. We can write net current density due to electron to be equal to now by using Einstein relation we can write mobility in terms of diffusion constant. The value of alpha is provided 0.1. You can see after putting the value, both the terms will cancel each other. Therefore, the net electron current density will come out to be 0. This question was not difficult, but many students get confused in the direction of diffusion and drift current. A better way to solve this question will be to first find the magnitude of drift current and diffusion current separately, and after that think logically in which direction drift current and diffusion current will flow. Like if you see in the first graph, this graph was provided for drift current only. By merely looking in the graph, you can tell that the electric field will be in this direction, and drift current due to electron as well as holes flows in the direction of electric field. Therefore, drift current will be in this direction. Now if you see in the second graph, since concentration of free electron is greater in the right side, therefore free electrons will move from right to left. And you also know that the current density is opposite to the direction of free electron. Therefore, diffusion current density due to free electron will be from left to right. So, you can see that drift current and diffusion current are actually flowing in opposite direction. You can solve the question either way, but I think it will be better to first find the magnitude and after that find the direction of the current, as it will reduce your chances of committing mistakes. We know the net hole concentration can be written as sum of thermal equilibrium hole concentration plus excess hole concentration caused due to optical generation. Also, you know that generation rate is equal to recombination rate for equilibrium or steady state condition, and recombination rate is equal to excess charge carrier concentration divided by lifetime of minority carriers. And since the silicon semiconductor is doped with n-type impurity, therefore the minority carrier lifetime will be of hole. You can write GL is equal to delta P divided by hole lifetime. Therefore, we will get delta P to be equal to GL into tau P. So, the hole concentration in n-type semiconductor can be written as P0 plus GL into tau P. Now, diffusion current density due to holes is equal to minus Q into diffusion constant of hole multiplied by concentration gradient of hole. Now you have to simply put the values. After calculating, you will find the diffusion current due to holes to be equal to 16 ampere per centimeter square. This is our final answer. For the second question, there is no need to solve the question, as first thing, I is representing the net current because it is not given that it is either drift current or diffusion current. But since I is the net current, we can simply say that I will be equal to 0, since Fermi energy level is a straight line occupying a single energy band. And we have talked about this earlier, that if the Fermi energy level is a straight line, it means that the semiconductor is in equilibrium, which further means that there is no current flowing inside the semiconductor. For the third question, here we have to use the formula which we derived using the Poisson relation, and we have charge density equal to initial charge density multiplied by exponential time t divided by relaxation time. Now you have to remember that the time which we take here is the time after the elimination has stopped, and you see that a pulse was incident from t is equal to 0 and the width of the pulse was 10 picosecond. Therefore, the elimination was stopped at 10 picosecond. We are supposed to find the charge density at 16 picosecond. Therefore, here in the equation we have to use t equal to 6 picosecond. Another important point that you have to keep in mind, that here the time which we have taken 0 in the charge density equation for reference is actually t is equal to 10 picosecond. Also, initial charge density or charge density at 10 picosecond is equal to charge multiplied by excess hole concentration at 10 picosecond, which is equal to 1.6 into 10 to the power 19 multiplied by 10 raised to the power 8, which will give 1.6 into 10 raised to the power minus 11 coulomb per centimeter cube. Now, charge density at 16 picosecond will be equal to 1.6 into 10 raised to the power minus 11 multiplied by exponential minus 6 divided by relaxation time, which is provided 8 picosecond. After calculation, we will get charge density at 16 picosecond to be equal to approximately 7.56 into 10 raised to the power minus 12 coulomb per centimeter cube.